In this lecture, we'll be taking a look at global fluvial processes, specifically deconstructing the concept of hydrology. Let's begin our discussion by taking a look at some basic terminology that relates to the work of hydrologists and, of course, geomorphologists. When we are taking a look at hydrology, basically what we are doing is we're monitoring or measuring or assessing fluvial action within a drainage system. One of the initial assessments that we have to make is or relates to the expression, a basin channel runoff. So we're estimating, even looking at this mathematically, we're estimating the quantity of water that enters a stream channel over a specified period of time. And when we start to look at some of the mathematics behind this process, I can't emphasize enough that time is probably the most important factor. Now, as we are starting to take a closer look at basin channel runoff, the other assessment that we as geomorphologists have to make is being able to assess water balance for a given landscape. The concept of water balance is really composed of three assessments. So if we were to define what water balance is in terms of how we measure it for a given landscape, we have to consider three characteristics or three units of analysis. The first thing we have to take a look at is the annual cycle of precipitation for a given landscape or a given environment. Now, this is generally done by volumetric measure, generally cubic liters. As you can imagine, measuring the amount of, in this case, precipitation that a landscape receives over a year in cubic liters is something that will give you a very large number. The next thing we have to do is take a look at or estimate the amount of water that's being lost in relation to the landscape. Now, water loss can occur through things like evapotranspiration. It can be consumed by humans and animals in a local setting, and it can be caught up in what is referred to as deep outflow. Deep outflow in this case is an estimate of the amount of water, again by volume, that exists within a groundwater system of flow. So the amount of water that is moving below ground through a landscape. Environmental assessment reports will often project this amount for a given space. They will define this by mapping that space out, identifying it, and then estimating, again, how much water is moving through that landscape below ground. And again, even when you take a look at environmental assessment reports as they relate to groundwater, it will also include even a direction of flow. So deep outflow, and this is something we'll return to again in this lecture, relates to groundwater flow, the direction and the volume. The last characteristic or the last piece to the puzzle when we're trying to estimate the water balance for a given landscape is an assessment of the annual fluctuations that occur in terms of soil moisture levels. And it's important to remember that when we're taking soil moisture levels, we're taking this throughout the landscape at different elevations. We're taking all of this data into consideration and then generating, in this case, an assessment by volume of the saturation of soils within a watershed environment. The next piece of the puzzle when we're taking a look at the hydrological nature, in this case of a local landscape, is to estimate channel discharge. And again, this is an estimate of water that is moving through sections, multiple sections of a given watershed. So again, when you think back to stream orders, we'll be taking a look and I'll have some visual aids for you to consider as you kind of ruminate on this. When you take a look at that drainage environment, that watershed environment, you're breaking the streams down into their orders, and you're looking at the geographical space that each of those segments of flow, are responsible for draining. When we are estimating channel discharge, there are some variables that we have to consider. And again, we're taking all of these measurements into consideration kind of holistically. So eventually all of this pieces together as we assess the overall volume of water that is flowing through a landscape. The primary variables are things like time, drainage space, and then the actual scale or the variations in elevation of the local landscape. We have to really take those three important pieces into consideration throughout the process of analyzing channel discharge. The most important tool in this assessment, and this is something that generally is available through local environmental agencies, are hydrographs for a system of flow. So you identify what part of a drainage system you're looking at, in this case a larger watershed environment, and then you pull hydrographs for that environment. And again, these are assessments of the space and the volume of material that's moving through a landscape over an annual cycle. So as we're taking a look, again, as geomorphologists, as fluvial scientists, uh, at a watershed, we're pulling hydrographs. What are we, again, essentially looking at? We're looking at fluctuations in the amount of systematic discharge for a watershed environment. These hydrographs, again, are taking a look at nearly all of the variables that we're considering, but again, the primary variables are the amount of water that is flowing through an environment and time. But hydrographs and the reports that accompany them will also include things like stream depth analysis, not just in the center of the flow, but across the flow. And then, of course, the study will report, self-report, the amount of time or the history of the flow that is being examined. Sometimes you'll see projections even into the future. Sometimes you'll see literally a century or more worth of data that is being compiled. Um, these can be very thorough reports, very comprehensive reports. The hydrograph, the discharge hydrograph, looks again at fluctuations in discharge plotted over time. As I said, the assessments of stream depth as they relate to discharge are also incorporated into this, and sometimes you'll see the expression stream stage that will be associated with these depths. Spatial variations are also extremely important when we're looking at channel discharge traits, and so we'll start to kind of dismantle these spatial variations within a flow, and this is where some of the mathematics now gets involved in the process. One of the initial principles that we have to associate with spatial variations is that in the majority rather of river systems, discharge increases downstream as one moves from a headwater environment to the larger truncated sections of a flow or eventually what becomes a river system. Again, moving from tributaries and then progressively adding more runoff until we get to that trunk channel. Now, there are a variety of variables that we have to consider as we are taking a look at discharge over a very large amount of space. This is an equation that is pretty common to the work of fluviogeomorphologists as they put together details regarding the again, hydrology of a watershed. Let's take a closer look at this. The most important part of this equation is identified by the letter Q. This is the stream outflow. This is cubic liters over time for a section of the flow. So we may be looking at, let's say, a first segment flow and assessing, in this case, the stream output for that area, the area that it is draining. And then we'll compare that. That may represent the I in this case. And then we may compare that to the next flow, one that's just down from that or downstream from that. That would be an I minus 1, and so on and so forth. So the subscript in this case identified by the letter I, and then associated with the function that eventually gives us a volumetric measure of stream output, that represents a segment within the flow, again leading from either a lowland environment to a higher elevation or vice versa. And the flow rate will always be reported in cubic liters over time. So there are some assumptions that we're making here. We have to assume in this case that all of the quantities in this equation can be determined with reasonable precision. So we have to draw upon a variety of resources, including instrumentation that we use in the field, to be able to assess these various variables or details in this equation. So when you're looking at stream outflow, what goes into this? Well, we have to assess um, the area that is drained by the segment. Again, we're looking at cubic meters or cubic kilometers of space, and then we are multiplying that by, in this case, the average precipitation, and we're subtracting, of course, the evapotranspiration rate there. So we take the average precipitation for an environment, we subtract the amount of water that's being lost by evapotranspiration, and this is a very natural process. We're not considering at this point any consumption of local water, and then we multiply that by that area drained by the specific segment, segment I, in that larger flow. Two pieces of the puzzle remain. We have in this case the groundwater outflow rate for the segment of the flowage that occurs just above the segment that is represented by subscript I. And then we have the stream output for the segment that occurs just downstream or at a lower elevation from subscript I, or the segment that we are studying, and ultimately the segment that we are estimating stream output or outflow for. So again, just kind of review all the pieces and parts here and juxtapose this equation and its findings, ultimately, to what you already know about stream order. Remember, just as kind of a review, as you move from a higher point of elevation within a watershed to eventually what becomes the river system associated with that watershed, if you're looking at that kind of watershed, you're moving from a very low number in a tributary section, in a headwater section, to, in this case, a higher number in terms of numeric value when we get to the actual output, or eventually the last truncated segment, the river segment of that flowage. Take a closer look at this diagram in order to start to get a sense of how that equation and its findings ultimately contribute to what we know of the hydrology of a watershed. You can see where the hill slope environments are. You have these kind of dotted lines here that in a sense represent the edges of an area that is actively being drained by a segment of the flow. You can see the channel networks themselves, and then eventually you see the basin and its exit. So just take a moment to kind of take that in and realize that as you move from the basin exit area, which would be the highest number, let's say a 4 in this case, to eventually what becomes these hill slope areas that have the small tributaries at high elevations draining the landscape, you're moving to a lower number. So the tributaries would be a 1, whereas eventually the river that contributes to the basin exit, where all of the outflow is occurring, that would be, let's say, a 4. So just take that in for a moment. This second diagram may seem a little bit more confusing. However, I think it gives you a better idea of how these first, second, third, fourth, and so forth order basins, and the systems of flow associated with each are interacting with one another in an almost systematic way. Then finally, in this last visual aid, we see how the natural environment interacts with the system of flow. We, in a sense, see a systematic relationship that exists within that landscape. So we see precipitation, we see the process of evapotranspiration, we see the interaction of these two forces and these two processes with the biomes that call a landscape, a hypothetical landscape like we have here, home. And ultimately we see an additional factor or variable in this case. We see the interaction of soil moisture with the outflow of a stream environment. And so what's really interesting about this is that even in the plants that are associated with the landscape, such as our hypothetical landscape here, the plants themselves begin to reflect uh, how this flow will change over time. And so the tree rings that are associated with uh, tree growth can tell us or be another resource for us to be able to evaluate how this system of flow has changed volumetrically over time. And we can juxtapose that with what we see in the current moment, taking all of the other variables that I mentioned into consideration. Let's consider a handful of other principles and concepts that are associated with the outflow of water resources within a watershed environment. So here are some of the principles that we'll want to keep in mind. First and foremost, when you think about how precipitation fits into this larger model, average patterns of precipitation will fluctuate as they encounter different elevations, or as we are working within a stream environment or a system of flow that may be at a higher or lower elevation to another portion of that flow. It's very comparative in nature. Another concept that's very important is that, and it again relates to precipitation, is that average patterns of precipitation will fluctuate with or in relation to regional expressions of climate patterns, so long-term patterns of weather or long-term patterns of precipitation and temperature. So we know that if we're dealing with a very arid environment versus an environment that may be, in a sense, humid, uh, we should see different patterns of flow. Evapotranspiration, a very important process, natural process that we have to consider as we're taking a look at some of the mathematics that hydrologists will, in a sense, apply to a landscape. We know that this will also fluctuate in terms of average air temperature or in relation to average air temperature. So in our equation, the segment of the equation identified by the label ET, evapotranspiration, this will generally decrease in terms of its volumetric expression as we see an increase, a corresponding increase in elevation. In relation to this, we know that there are a handful of other principles that need to be taken into consideration. A lot of these principles come from literally decades of research in portions of North America having to do with the study of stream flow. Groundwater, in this case, a very important part of our overall assessment of output, will also fluctuate. And it will fluctuate in relation to some of these other variables. So, for example, if we take annual patterns of precipitation and we juxtapose that with, in this case, the overall output of a water environment, if this is greater than the average or annual expressions of evapotranspiration for that landscape, we know that we will have an imbalance. We will have a very dynamic expression of equilibrium within that landscape, and the groundwater outflow will, in a sense, increase because we'll have more groundwater available as a resource within that landscape. This brings us to another equation, very similar in its overall numeric structure and in terms of what variables it's incorporating into the function itself. And that has to do with groundwater and the flow of groundwater through a landscape. Take a moment and look at this equation compared to the previous equation, and you will see that there are very similar forces at work here. For example, we're still comparing and contrasting the measurements of precipitation and evapotranspiration. We are multiplying that by the amount of physical space that segment of flow is draining, and then we are taking that interaction and we are adding, in this case, the groundwater outflow of the previous segment, the segment in this case just above the segment we were studying. We're then adding the overall output of that same segment and the projected output for the segment that we are currently studying. Sounds confusing, but when you take a look at the equation and really process through it and look at those subscripts and tie them back to, in this case, stream order, I believe it will make more sense. Again, in relation to what we are seeing with groundwater, there are a few other ideas that we have to keep in mind. Again, as we take all of this into consideration holistically, one of the very important resources that we're always monitoring in relation to outflow, whether it's in groundwater or if it's in the system of flow, the larger system of flow itself, we have to consider the idea of recharge. So when we're taking a look at volumetric measures of precipitation and evapotranspiration, if we subtract the evapotranspiration from the annual patterns of precipitation, we will get another resource to use as an assessment tool for a segment of flow, and this would be groundwater recharge. And this becomes very, very important because, again, if you take the human and animal component out of the assessment, it really gives us an idea of kind of the long-term plan or the long-term future for that system of flow. Will there be a groundwater expression that is similar across time? Of course, when you start to take a look at the demands that local plants and animals are placing on that groundwater resource, that will fluctuate. But in its bare bones expression, the groundwater recharge that we are looking at and using as an assessment tool for a segment of flow will consider the interplay mathematically of precipitation and evapotranspiration. And then finally, in terms of things we need to consider as we're putting some of these ideas together, if you're to take the overall output or outflow of a system of flowage, a segment of a larger water basin, and you are to divide that by the groundwater recharge rate, again on an annual basis for that same geographic space, if that ratio is less than 1, we know that the watershed is considered to be a groundwater exporter, meaning we will have an adequate amount of groundwater available to us, or we will have a surplus of groundwater that will be expressed in an increase in the groundwater outflow for that, again, segment of the flowage. Okay, so let's look at some kind of big picture ideas here with regard to the global process of fluvial action. First and foremost, we know that, and it's always good to compare and contrast these forces in more extreme expressions. In arid regions, water losses through evapotranspiration and seepage can lead to downstream discharge decreases. So the idea here is that the interplay between a climate type, especially a very dry climate environment, and the variables that are at work in that climatic expression, these players, these variables that are interacting with one another will also have a pretty significant impact on the discharge in that system. Additionally, on a global level, things like river discharge are closely related to the balance between atmospheric patterns, long-term atmospheric patterns of precipitation and evapotranspiration. So for example, the highest output discharges that we see globally are generally achieved under very humid climatic conditions. And when we get to climate and we take a closer look at climate regions and their nature, you'll see some of the forces that are contributing to these very high discharge rates. We also find ourselves, or when we find ourselves rather, in a humid, warm, mid-continental region, similar to areas just to the south of us, stream discharge rates are generally higher than what we would expect in northern environments, or as we begin to move in terms of latitude to the north. And again, things like elevation will be sometimes confounding variables in this process, but generally that's what we are seeing. So in places like Southeast Asia and mid-latitude mountain ranges in locations such as modern Chile or Scandinavia, we see pretty high outputs with regard to stream discharge. And we see this across all of the different stream orders that are associated with a system of flow. In this case, Scandinavia is included due to the high elevations of its mountain belts. In the south, we recognize the Småland Plateau as a very good example of this. Its discharge is recognizable in the lowlands or plains of, in this case, Skåne, leading to southern and coastal portions of what is today modern Sweden. So if you're looking for geographical examples, I think higher elevations in both Chile and what is today Scandinavia provide really good examples of how elevation is also part of this interactive network. So all of the things that I've been explaining up to this point have really addressed spatial variations and variables as they relate to how we assess output in this system of flow. Let's take a look at some additional temporal variables and how they may in some way, shape, or form contribute to what we're seeing in the field. Out of everything we have discussed and described up to this point, I cannot emphasize enough the importance of time. Time is an important factor or variable in any assessment of landform analysis and change. In the case of stream discharge, time is assigned to seasonal variations in patterns of precipitation and, of course, atmospheric temperature. These provide, again, the basis of our modern climate models, chiefly the Köppen climate system. The measure of what is referred to as river regime is assigned to this temporal variable. River regime, in a sense, is a time-specific measure of stream discharge for a watershed. River systems in humid environments will experience the most significant temporal variations with regard to stream discharge. We will see almost constant and dynamic expressions of systematic equilibrium in these watersheds. We'll see heavy winter precipitation patterns, and we will see the impact that convection storm activities or actions take during the spring and summer months. When it comes to these humid environments, we see a very important idea that as geomorphologists, as climatologists, as hydrologists, looking at long-term patterns and studying natural phenomenon over these long segments of time, we see the impact that storms and convection air currents and the weather associated with them have in terms of studying stream discharge. Generally, this will result in the creation of separate hydrographic models for watersheds in these more humid mid-latitude environments. So we'll see what are referred to as storm hydrographic models being assessed for these systems of flow. Generally, what happens here is recorded storm flows and recorded storm activities are compared in contrast to long-term base systems of flow, even estimates for time and discharge rates in a flow environment. And that occurs generally for an entire drainage basin or a network or system of streams that are part of a basin environment. There is another important mathematical principle that hydrologists have to assess as they are incorporating storm hydrographic material, what is referred to as reoccurrence or reoccurrence estimates are generated for systems of flow in these more mid-latitude humid environments. Generally, it's a temporal expression of storm and precipitation magnitude as it relates to long-term patterns in the environment. So they're comparing extremes to what is understood to be common or everyday occurrences within a system of flow. In this case, we have an equation rather that generally is utilized in the field, n plus 1 over r. This is again our reoccurrence estimate. This is where n is the number of total flood level events that are occurring for a stream environment annually. And then r in this case is the recognized ranked magnitude of storm events. So it's an equation that allows us to take a look at the number of naturally occurring flood events within a 12-month period, and we are able to, in a kind of a ratio format, juxtapose that to the recognized ranked magnitude events that will occur as part of a storm activity within that same environment and over that same period of time. So again, natural flood environment or natural flood events over storm events. And so this ratio provides us with another tool, another resource for being able to assess where a system of flow is in a long-term pattern of dynamic change. If you're dealing with a watershed in a mid-latitude, equatorial, subequatorial, humid environment, humid warm environment, you know that you're dealing with a system of flow that is very dynamic in its nature, comparative to, or in comparison rather, to other systems of flow across the planet. So this tool allows us to compare and contrast normal patterns of dynamic expression to storm-based dynamic equilibrium patterns, patterns that may cause a major shift in the overall flowage for that region. So again, comparing and contrasting things that are more natural, more predictable, expected to the contributions of a storm environment. Here too, soil moisture has to be considered over a long-term period. In this case, we look at soil moisture no matter where we are in our study over a 12-month period. And in these more dynamic climate environments where we have the interaction or the contributions rather of storms to an overall system of flow, magnitudes that take a look at discharge at bank full and the amount of soil moisture that is present in those bank full environments where we have a river, for example, reaching a flood stage. These are also very important measurements, moisture measurements, to be able to record and compare to what we believe to be normal patterns of soil moisture for that same system of flow throughout periods of time when we're not out of sync or when we don't have some sort of extreme weather event. So again, the kind of moral of the story here is that when we're looking at a system of flow and we're trying to get a sense of where it currently is and eventually where it will end up in this change over time kind of model, we want to take into consideration both spatial and temporal variables. However, with that said, we also have to take into consideration the impact that the location of a system of flow has on the overall output of the system, and any and all abnormal or not commonly predicted kinds of events within that geographic region, how that may too contribute to the overall output. And this is the power of the work of hydrologists. They take all of this into consideration to be able to assess where we are in the overall evolution of a landscape and where we may be going in terms of a floodplain or river or watershed environment.